So today we're going to be talking about compression, right? So if I have this bit of timber, tension was pulling, compression is squashing, right? And you can immediately see what's happening with this really, we call it slender. So the ratio of, let me just check this is a copy. Yes, because I'm going to doodle all over it. So if something, this is the basic premise of it, but if something has like a certain length and then it has a certain, let's call it depth, right? Or width, if this is like rectangular. Okay. The basic premise is if the L to D or L to B ratio is too high, right? Slenderness is referring to length to that cross-sectional dimension, right? It's going to do this, it's going to buckle, okay? Now buckling, I think I mentioned this last week, buckling is elastic, so I can undo it actually, but it's going to cause an early failure compared to what the material should theoretically be able to take in compression. You know what I'm saying? So it's going to, you can see that it's like about to snap basically, right? Because it almost has like this bending stress induced by buckling, right? Oh, nearly broke it. Okay. So, yeah, that's the general premise of buckling, and we'll talk about buckling and slenderness ratio first before we talk about compression design, because buckling is a huge part of compression design. Okay. So, Euler buckling. So there's actually two types of buckling, okay? The one we're going to be talking about for compression, or today, is called Euler buckling. So that's when you have an axial force, like compression, being applied on your member, right? So this will happen for like columns, and it might even happen for like trusses and stuff like that, okay? So wherever there's compression, because last time I talked about how there was like columns that experience compression, and there's truss members that might be in compression. Yeah. So like for example, that column there, it's taking all these loads, being compressed, right? And then you'd also find compression in like truss members as well, right? So this is important, and this is from like solid mechanics and stuff. You might not remember it that well because it was at the tail end of solid mechanics, so you might have been like locked out already or whatever. Okay, so I'll give you a bit more context, right? Because we're going to want to differentiate the kind of buckling that you see in steel beam. Just like steel members. Okay, one is local buckling. So that's the cross section, and you can see that. Oh, actually, you know what? I kind of group these together to be honest. But basically, it's where, let's say you have an I beam, or sorry, I column or something, right? And then into this section, you get that compression force, right? So like as we're looking at it, imagine there's a force being applied on this section. What you'll start to see is that it's gonna start buckling like that, right? So it might buckle at the flange, or it might buckle at the web. And there's different formulas to calculate it. You'll see later. But that's local buckling.
So where is the force coming from?
Into the page. Because it's compression, right? So this is the cross section of a column, right? So we're looking like bird's eye view at a column. So into the column. That's compression, right? And then there's global buckling, right? So global buckling is more what's happening from what I'm showing you here, right? It's where over the entire length of your member is where it starts to buckle out, right? Whereas for local buckling, it might be like, that's one flange, for example. Say that flange has width of flange or whatever. And here is like TF, the thickness of the flange, right? Now instead of length to depth, right, we're comparing flange length basically, or flange width, let's just say, to flange thickness. Do you know what I'm saying? So this is a different way of looking at it, but both are experienced in compressive stresses, right? Okay, the other one's flexural buckling, which I'll talk about after you guys have done with your quiz, because that's for the flexure part of this course, which is like week 4 and 5. Okay. All right. Do you have any questions? So that might be what local buckling looks like on a column.
So PF is just flange is like the whole thing.
That's a good question. So basically, we talk about parts of a cross section, like an I-beam, in terms of flange and web, and it's usually based on like width. So that's the web, because the width is the thin one, right? But this whole thing here is a flange, and that's a flange, right? Because the width is bigger for a flange, right? So that's the width of your web, that's the width of your flange. You get what I'm saying?
And then the calculations
You'll see later, but yes, basically it's because this is like cantilevering. So that's the bit that is only supported on one end. Yeah, that's why you do it like that. Okay, but yeah, global buckling, yeah, it would be like over the entire length of the member. It's being squashed like that, and it does this whole thing. Okay, yeah. I won't go over this page as much because it's more context, but this is the Euler buckling formula. Okay, and you would have learned this in solid mechanics towards the end. But yeah, basically he derived it, and it's a function of pi squared as a constant, and your elastic modulus, and your moment of inertia, right? So that's flexural rigidity, and then this is your effective length squared. Okay, so we'll talk about effective length towards the end of this session. Okay, yeah. But for now, just think of it like, if that's your column, just think of effective length as the length of the column, for example. Okay. Okay, cool. Yeah, so yeah. This is just the simplified version, and I think I already kind of briefly explained it. Just your ratio of your length to width, basically, right? So I'll give you another example. This one, right? So you can see clearly this is like a ruler shape, and so it's much longer in one cross-sectional dimension than the other one, right? So let's just say its depth is a lot higher than its width. Okay. So if I compress it, which way do you think it's going to go? Based on what you guys can see. If I press in like compression, yeah, it's going to go out like that way, right? Is it ever going to go up down? No. So you have to keep in mind that when you have a cross section that isn't necessarily symmetrical on both, like when you rotate it 90 degrees, like this square, it can buckle out. Oh, sorry, it's not more likely. It will buckle out in the direction that's significantly weaker. So the minor axis, right? So the major axis, remember, is this depth, which is like really high. But the minor axis is the one that's weaker, right? So it goes left to right.
Oh, so it's not necessarily x or y, it's whichever is weaker.
Yeah. So if I was to flip it the other way around, which way is it going to go now?
Up and down.
Yeah, it's a weaker dimension for buckling. So if this was a column on the ground,
Yep.
it's going to go that way, right? Makes sense? Okay. But we use something like one step more complicated than length to depth, right? We use effective length to radius of gyration. Okay. So radius of a gyration has this formula. It's the square root of your moment of inertia over a. But you'll see that there's Rx and Ry. Okay. So radius of gyration, x is moment of inertia x over a square root, and then this one is the one with y, right? It's actually a very hard concept, in my opinion, to explain, radius of gyration. It's actually very easy to just look at the number and accept it and be like, okay, that's the radius of gyration. It's much harder for me to like explain like physically, to be honest with you, but I'll try. So let's just look at that kind of ruler shaped cross section that I've been showing you guys, right? And we have XX bending, which is your major axis bending, but we also have YY bending, which is the weak axis, minor axis bending, right? And we're going to talk about it in terms of bending, because buckling is basically just compression that induces. Yeah, buckling like it kind of acts like bending in terms of what stresses it puts on your member, right?
So the way that it will bend is the minor axis.
For this Cross section, yes.
Oh, okay, so that's not.
I'll get to that. Okay, so basically, radius of gyration. It's kind of cooked, right? But I think of it like it's like a radius. Actually, no. To be honest, this is a bad explanation. I think radius of gyration. Firstly it's in millimeters, right? But it's kind of like a ratio of your inertia, right? So this way is like BD cubed on 12. It's a ratio of that by your area, right? Your overall area, and then you square root it. So it's hard to explain like where it comes from. Okay, but just note that a bigger radius of gyration basically is stiffer, right? It's proportional to your inertia, right? So a bigger radius of gyration is stiffer, and it's less likely to buckle that way. Not as less likely. It won't buckle that way, okay? Do you know what I mean? So which radius of gyration, based on what you can see here, is bigger? Rx or Ry? So Rx is bigger, which means the slenderness ratio is lower. Because it's divided, right? That. So if you have a higher stiffness, right, radius of gyration, it's going to cause the slenderness to be less. So it's more slender in the left-right direction, the minor axis direction. Whichever one is lower is more slender and is the minor axis, yeah. Yeah? Okay. What else? Okay, but that's not the full story, because you can have, you can basically have, like, sorry, Farhan, can I actually have your assistance here for a demonstration? Yeah, just come up. You can have constraints, right? Okay, so can you hold it with your arm in the middle, like that? So if he holds it like that, it can't bend like a C shape. It has to bend like an S shape, right? Yeah. Can you guys see that? Yeah, so let's do it like column way. Do you see how it's bending? I'm just gonna check if this fucking camera's working.
Can I see?
1 sec. Okay. Do you see how it bends in an S shape now? Yeah. So basically, we've halved the effective length in the minor axis direction. But because this is so different in terms of the depth versus the breadth, it's still going to bend in the minor axis direction. But if they were more similar, so if this was more rectangular, more like a block, then you kind of have to compare which one's going to fail first, the minor axis or major axis bending. Thank you, that's all good.
No worries, mate.
And if you were to constrain it in 2 spots, it would make like a triple S, you know what I mean? So, yeah, for slenderness, you have to check effective length, basically, right? Okay, it's a general idea. Critical buckling zone, slender member. Yeah, so, oh, sorry. Oh, yeah, my bad. Let's make my face smaller there. Oh, yeah. Yep, okay, cool. So, basically, a more stubby member, let's say my drink bottle, okay. There's a certain amount of, imagine like a hydraulic press, just like going on this drink bottle. There's a certain amount of like compressive force before the whole thing like squashes, basically. So that's like a squash yield failure, right? That's material failure. But we know that that won't be the case for something like this, something that's really like stick-like, because it's gonna buckle and break before that happens, before it reaches material failure, right? So what we say is for short members, like this drink bottle, we don't reach buckling, right? We reach yield crushing. There's a few words for it, but yeah, like yielding in like a squash failure first. Whereas this one, you would reach buckling first. Does that make sense? Yeah, cool. All right. So for compression design, right? We have to take this to account, but we have different words to explain it. So firstly, from last week, you kind of hopefully have a grasp of, sorry, I'm going to zoom in. You hopefully have a grasp of what NC star is now, right? So NC star is the factored compressive force, right? So for example, you have the column, right? And then that force there, right? And then that reaction, or whatever, that's the compression, okay? For section failure, we're going to check two things. We're going to check material crushing and we're going to check local buckling. But then for your member failure, we're going to check global buckling, right? Which is how many constraints it has, or yeah, and all that, and check the slenderness ratio and stuff. Okay, cool. So, oh, and sorry, one more thing to note. The capacity reduction factor is 0.9 again, just like tension. Okay. All right. So, okay, here's some pictures that I drew, and hopefully it illustrates the two failure modes. So the first one is a material crushing failure where your drink bottle, right, would squash, and you can see that it has this like wrinkly thing that I drew, right? So that's a squash failure. Okay, the next one is local buckling. So this wouldn't really happen for the drink bottle because this happens more for thin sections like an I-beam or whatever, like something with thin web or thin flange, where it locally fails, like here or here, or in some cases the web. Right? Does that make sense? No buckling is involved for the first failure mode. The second failure mode is a local failure. So it's if a web crushes. Yeah, if the web gets crushed, what's called crippled, or sorry, that's the web, or if a flange gets crippled. You have to check for all those things with the first failure mode. For the second failure mode, now instead of looking this way, we're looking at the overall beam, right? Because before this was this section, right? Now we're looking at the overall beam and seeing whether it's going to fail like that, right? Or that, or whatever, like this is assuming compression or whatever, right? Okay, so that's what we're going to run through slowly. Okay, so the first formula is NS is KF times AN times FY. Okay, so we're going to go through these one by one. Form factor is the hardest to explain, but it's also the easiest to get if you're dealing with a standard section. Okay, so I'll talk about that maybe last. AN is your net cross-sectional area. So that's your gross area minus any bolts that you might have. Okay, and sometimes they have something called the negligible whole area rule, where if for example your column was like huge and then there's only like a tiny bit of the areas taken up by bolts, you might just completely ignore the bolts. Doesn't really matter, right? But then this is just like a rule to say when do you actually consider the bolts or not, right? A lot of the time that I've found, I just use AG when doing compression design because bolts don't take up a huge amount of cross-sectional area for compression members. The reason this is different to tensile members is a lot of the time tensile members might be like a bracing member, for example. Okay, this is kind of like going into a long explanation, but like imagine you have a warehouse, okay, and this is a top-down view of the warehouse, and that's the ridge of your roof, right? So this is the roof of the warehouse, and we have all these different bays and stuff, right? You have bracing members on a roof, for example, where you want to stop wind forces that are hitting the edge of the building through tension. Okay, so this thing's like bracing this structure. Anyway, there's like a lot to talk about there, but that's an example of where there'd be tension, right? So in those cases, you don't actually have very big structural members. They're kind of secondary members, so they might be in the form of an equal angle. Okay, an equal angle compared to a bolt right? The bolt takes up a lot more area. Say you're attaching one to a plate or something. The bolt takes up a lot more area in that equal angle than it does in a big eye section. Does that make sense? An equal angle is like a small thing, right? So you have a small thing, I don't know, like this marker or whatever, and a bolt is like only the size of a bolt, right? And it's going through it. It eats up like a high percentage of that area, but for like a large section, a bolt doesn't take up as much of that, relatively speaking. Do you know what I mean? So that's why we use AG a lot of the time as AN, right? So there's this rule to say, yeah, it's negligible, basically the whole. All right, that's like a long-winded explanation, but that's to say, that's all to say, oftentimes we just use AG in this formula instead of AN. All right, FY. Basically, it's a yield strength, right? But it's the minimum yield strength between the flange and the web. So that's the flange, right? And that's the web. And what you might find is that the flange will have a yield stress, let's say, of, I don't know, 320. I was making up this number. But the web might have one of like 350, right? Because the web is thinner, right? And as it cools down, I think I might have mentioned this briefly in the crash course, but as it's cooling down from being hot rolled and all that, the air kind of like cools it down more evenly because it's thinner than the flange, right? Whereas the flange will have like heat that, you know, is exposed to the air and then it cools down, but then the middle is like still hot and stuff like that. So actually it's like worse in terms of its mechanical material properties. Yeah. So you would take the minimum basically because you want to be conservative with this course. So you're taking the minimum between the flange and the web. Oftentimes I find it's the flange. Yeah, is the minimum. Okay, but yeah, you can get that from that table that I included in my previous weeks of notes. All right, so real quick, I want to show you OneSteel because I haven't pulled this up yet, but you can find OneSteel online just by searching OneSteel catalog, and it's a book, and it has all your standard shapes and sizes for different products, right? Right at the top here, you'll find universal beams, right? Oh, sorry, there's like there's welded beams and welded columns, and then you have universal beams, okay? So here we'll have something like 610 UB 125. So the first thing is its depth, right? Let me see if I can find the row. Oh, here we go. Depth of section, right? So it's going to hover around 610. It's just a description of how deep it is, the beam. And then 125 is how heavy it is per linear meter. Okay. And then as you move down the page, you get to the next set of beam depths, right? Which hovers around 530, and then 460, etc. Okay. Sorry? Yeah. It's the depth of the overall section. Yep. But you'll find that on OneSteel, you can quite easily find. Sorry, it's on the next page. You can quite easily find KF. Okay. The form factor, which is what I will talk about in a second. But it's already pre-baked. It's given to you, right? The only thing you have to really consider is whatever section you're looking at, whether you're talking about 300 plus steel or 350 grade steel. So these are just like different manufacturing grades, right? But it'll tell you in the question which one to do. But like, so for example, it would be like 0.888 or whatever, right? Which seems like happy days because it's like, okay, well that's just the number that I plug in, right? But where it gets complicated is if you have to calculate this section yourself, right? So if it's not in OneSteel catalog, right? You know how I said OneSteel catalog, it has a bunch of standard products similar to Legos and how Legos come in standard sizes, right? What if you wanted to make your own Legos? What if you wanted to make Legos that were like unique shapes and sizes, right? Then you have to recalculate this value, KF. And it gets really AIDS. Okay, so for example, we want to make our own I-beam, right? But instead of the standard shapes and sizes that it comes with, we just pick random numbers, right? Which, at least last year, this was like one of the assignments. because calculating a custom section takes ages, basically. Okay, so that's a custom section versus a standard section. A standard section is what you'd find in like OneSteel or whatever. OneSteel, by the way, is just one company that documents all of the steel products, but you'll find, and it's an Australian company, but you'll find that other manufacturers also document all these beams as well. So like, it's a different company that manufactures it. Osrio, like for example. Oh no, sorry. So Osrio is for rebar. Okay, OneSteel is probably the best bet for information. But yeah, anyway, yeah.
Like the different manufacturers have different numbers as well.
They're universal.
They're universal.
The only difference is which products they sell.
Oh,
So, for example, if we look at
so the ones
Here.
catalog is what they sell.
Yeah, it's a catalog of their items, the products, right? But for example, like these are pretty standard. What might not be standard is like, okay, do you see how like universal columns, right? They go down as small as 100. So OneSteel doesn't sell like, for example, a 100 UC 10 or 12 or whatever. It doesn't sell anything smaller than this. But there are other steel manufacturers out there that would sell ones that aren't listed here. Do you get what I'm saying? But these are, OneSteel is like some of the most common in Australia. But if you go to like UK, you can basically find the exact same products. Sometimes like the numbers might be like a few decimals different. You find the same ones, it's just, you have to figure out whether they supply it in whatever area of the world that that you're part of and you're designing for or whatever, right? Does that make sense? Okay, so when you're starting to calculate KF, there's two things to keep in mind. There's effective area and gross area, okay? So basically, certain areas of a section might be prone to buckling, local buckling, okay? So if you're looking at this shape, here's the general like way that you think about it, right? On how many sides is it supported? Okay. So if I look here, this kind of intersection between the flange and the web is not going to buckle because it's supported on all sides, basically, on three sides. Similar idea here. Okay. So these are unbuckleable areas. The furthest points from these areas is what's going to buckle. Okay. So here we have this portion of flange, and it's basically cantilevering. Okay. If you think of force going in and out of the page, right? It's a cantilever, right? It's only supported on one side. Okay. The web, right? It's supported from here to here, but it's basically simply supported. Yeah. And then it's taking forces, compression forces, in and out of the page. Does that make sense?
Wait, isn't that too?
Yeah, it's not really simply supported. That's the wrong word. It's more like rigidly supported, but on two sides. Yeah. Does that make sense? Okay. So we kind of know the weak spots are like here in the middle, right? Because if you think of max deflection, it's going to be in the middle, right? For a simply supported beam, or like a beam that's rigidly supported on both sides, or cantilevering, it's the free end, right? That deforms most. Okay. So here's the logic. Okay. Basically, we're trying to calculate the area that's not buckled. Okay. So everything that I've highlighted in red, it hasn't buckled, right? And that's AE, basically. AE is the effective area, so the non-buckled area. Okay? That's what we're aiming for in the end. But the way that we calculate it is we have to look at each individual element that's unique. So if you look at this shape on the left, there's actually only two types of shapes that we have to check. Right? We have the cantilevering flange component, and we have the supported on both ends web. Okay? Alright, so like I mentioned before, the way that we do it in the Australian standards is we compare its width to thickness. Okay? So its width for this flange element, right? The way that you do this is you go 400 minus 100 divided by 2. So that's 150, right? Oh, I mean, I actually wrote it here, right? But that would be B1. This would be the thickness, that'd be T1, right? So that's element 1, does that make sense? Okay, for element 2, right, let's do the same thing. We're comparing its width, right, which is 300, by 100, which is its thickness, okay? So if you think of this like as the beam thing, right, we're doing length by depth, basically. Well, like, I know we're looking at it from a different angle, but that's essentially what we're doing, right? We're doing width by thickness instead. Okay. Okay, so now we calculate the slenderness, right? And there's two formulas that's documented in the standards, AS4100. Oh, by the way, I forgot to do this. If at all you want to look through the standards, I've got it printed out. Yeah, then we'll go for it. Yeah, AS4100. So this is the steel standards.
The latest one.
Yeah, it's 2020. Yeah. Good question. Good question. Now Farhan helped me print this out. Yep. So chapter 6 is axial compression. So if you want to look through like what these formulas that I'm talking about, then so just pass it around, share it, be nice and stuff. Okay, so we're gonna talk about two shapes. One's plates and one's circular hollow section. So anything that's rectangular, we're gonna call a plate, and anything that's a circular hollow section is like a hollow tube, like a pipe, basically shape. Okay, so plates. These are all plates, basically. What we've talked about so far are just a series of plates, right? The hollow sections is there's not really a good example, but like, yeah, we just use we use a different ratio. We use the outer diameter by the thickness of that hollow section. And yeah, we do something else with the square root. These are empirically found formulas, by the way. They did just like a bunch of lab tests, and it's like, this is the best, these are the best numbers to predict the behavior of it, right? So that's effective slenderness, right? Oh, sorry, element slenderness, okay? So this is important. It says lambda, but it's subscript E, right? Because right now we're just talking about elements. We're talking about the flange element or the web element, okay? The slenderness of the element. Yeah, and then we have two elements, right? So we're going to talk about slenderness of element 1 and slenderness of element 2. And we're going to compare it, okay? So another term you have to look at is the slenderness of the element, the yield limit, okay? Okay, so these are, again, in AS4100, and what it's saying is at a certain slenderness ratio, it's going to yield, okay? So remember, slenderness ratio, bigger slenderness ratio would be like this this kind of twig shape, and it's very slender, right? And a lower one would be like this drink bottle, okay? So higher means more slender, okay? So, if, for example, and this is like the whole cantilevering or supported on both sides thing.
Oh, so if that value, the yield slenderness limit is higher than
I'll get to that. Yeah, all good. So, okay, let's just break down this table, right? So we have flat shapes or plates, and we have circular hollow shapes, okay? So from the flat shapes, we know that that there is a cantilevering one and one that's rigidly supported on both sides, right? So going back to that example, right? This one was outstanding or whatever, an outstand, cantilevering. And then this one was supported on both sides, right? So they have different values. So these, by the way, come from the question. And I think, these are the types of manufacturing process involved. So SR is stress relieved. Very common is hot rolled. So I-beams are hot rolled, for example. Welded plates and stuff. That's like if you literally get a welding torch and you weld like here and here and here, lightly welded, heavily welded, whatever. Cold formed. So hollow sections and square sections and rectangular hollow sections are cold formed, right? So they're formed at like closer to room temperature than like boiling, basically, right? This is the manufacturing process, right?
Is the square sections are they what outside?
Oh, so see if I'm for the square ones. Square ones would be 4 plates. Yeah. Oh, sorry, not outstands. The this one.
Oh.
Because in the corners, that's unbuckleable, right?
Oh yeah, they're all yeah.
Yeah. So that's a good question though. Like the square ones are basically a series of flat plates like that. Yeah. Okay. So the other thing is just have a look at these yield limits, right? So you have to think about this because there's a couple of layers to like bounce back and forth between, right? So okay, let's look at hot rolled only, comparing the numbers again. So hot rolled, cantilevering portions like the flange, for example, here, is 16. Okay, that's the lowest limit, and then the supported one on both sides is 45, and then the hollow section is 82. Okay, so here's where you have to think about it for a second, right? We know that something like this stick has a high slenderness, right? And something like this has a low slenderness, right? So remember, this is a yield limit. How come the cantilevering one, let's just compare the cantilevering one to the one supported on both sides. How come the cantilevering one's a lower slenderness limit? Wouldn't you think it's the other way around? Isn't that a bit funny? It's because the limit is like, so that's the limit, right, of these 3 numbers, right? But as you get more and more slender, that's where it buckles, right? So it actually does make sense if you think about it. For something like this to buckle at a really low slenderness, right? Because it doesn't take much to buckle, right? Even this could buckle potentially if it was only supported on one side. Do you get what I'm saying? Yeah. And then for this one, it's a higher number, and then for the circular hollow section is the highest number. So circular hollow sections, right? So imagine I had like a pipe and I was compressing it. It's not prone to buckling, to axial buckling. In fact, generally speaking, like circular hollow sections and what's the other one? Square hollow sections and stuff are used in like structural engineering, like they're selected because of their property of being very resistant to buckling.
So wouldn't it be better to choose circular?
They're more expensive to manufacture. Yeah. It's a good question though. Yeah. But they're prettier as well. People, like architects like to have circular hollow sections sometimes because like this, it's prettier column or whatever. Okay. There's many reasons to select. I'll give you an example. Like someone that was working in my company was designing a sports gymnasium, and they were designing like this truss that supported that structure, right?
Yeah.
But it's like an indoor sports gymnasium where people get balls and stuff stuck up in the roof and stuff all the time.
Oh yeah.
And so they selected circular hollow sections because a ball bouncing on a circular hollow section doesn't get stuck.
Yeah.
Do you know what I mean? So that would be like a netball or whatever, or a volleyball, let's say. It doesn't get stuck, so it rolls right off. Whereas if you had an I-beam that was selected, your ball might get stuck there or something. So there's many reasons to select different types of sections, and sometimes it's a logical reason like that and not a mathematical reason. Do you know what I'm saying? So yeah, hope that's interesting. Okay, so moving on. We also have to calculate the effective width of each section. So the effective width is basically these two combined, it's the width of the portion that hasn't buckled. And for this element, it's this one. Do you know what I mean? Let's just call that A and B. So it's like the A portion and the B portion added together, and this one's the not for the purpose of buckling check. I think you would for AE, which is the next step, but here we're literally just trying. The formula spits out this basically. The formula spits out what portion of it remains. So we actually ignore the blue bit. Yeah.
Wait,
So this is the unsupported width.
so there's BE.
So the unsupported width, right? Because that's all supported. This is the unsupported widths over here. Yeah. So that is that. Okay. That's that formula. And then circular hollow section is similar, but you have to do two checks, right? So it's the minimum between these two. And that's basically that. So that gives you BE, right? So basically, through those formulas, you're going to find BE, right? So we know that that portion is the unsupported portion of that, and that's the unsupported portion of that. And going back to your original point, like in the end, we actually want to find AE, right? But here's where you kind of just have to draw it out, and it's like a very visual process because you don't want to double count anything anyway. So you kind of want to just figure out, okay, that's BE on that side, that's BE, like this is the same one, and then we're going to add on that 100 mil again, and then you kind of just like add these blue rectangles together. So it's a very like, there's not like one way to do it because you have to kind of use your engineering judgment to figure out the AE in the end, right? All right, so AE plugs into KF, right, in this ratio formula. And by the way, AE is always less than AG because say that's like 80, oh no, that's a bad number, 800 mil squared. AG would be like, say 1,000, right? And then KF ends up being like 0.8. So if we go back to OneSteel, that form factor was like 0.8 or 0.9 or whatever, right? That's the portion that hasn't buckled. Does that make sense? Yeah.
So that's basically saying 80% of it doesn't buckle.
Yeah. Due to its doesn't locally buckle due to its this inherent shape slenderness. Yeah. So what they're actually trying to do when they're finding the ideal dimensions of these shapes is they want to keep this number as high as possible, but not over design it as well. Because you could just have like an enormously stubby I-beam, right? But that's like super impractical because it's heavy as fuck and you're wasting a lot of material. So they want to keep it as thin as possible while not buckling as much as possible. So that's how they like ended up basically finding the perfect shapes. Do you know what I mean? Okay.
So I think I'll put the 88.
That alongside all these other things. Like for I-beams, there'd be a lot of manipulating how moment of inertia works because I-beams are usually to do with bending resistance. So there's many factors, but that's one of the factors, right? Okay. Anyway, so that goes into this formula. That's usually AG. That's the minimum between your web and your flange, right? And then happy days, and then you get this times by 0.9. See if the capacity still can withstand the forces, and then once you've checked it and it's all good, then you're you're good to go. So that's NS, okay? Okay, NC. Do you guys need a break, by the way? I think we'll just try power through if that's alright. Unless you guys gotta go get water or anything.
I gotta go.
Sorry? Bathroom?
I got a workshop.
Oh, okay, no, that's all good. Thank you for coming.
It's recorded, right?
Yeah, it'll be recorded. You can just check out the second half, yeah. But yeah, thanks for coming. Okay. All right. Other thing is Euler buckling. So that's this whole global situation that's going on, right? Okay. So basically, you take the capacity that you found out in the previous step, and you multiply it by this alpha c constant, essentially, right? So what is alpha c? It's the compression member slenderness reduction factor. Okay. So this is found through a few more steps, basically, right? Thanks, man. It's Kai, right?
Yeah.
See you, Kai.
You also on standards or something we calculate.
It's something we calculate. So this one, you always have to calculate. NS is a lot simpler because a lot of the time when you're dealing with OneSteel products, KF's given to you. So it's actually very simple to get. Alpha C all depends on your lengths. Because no one's going to tell you how long your beam is, right? The standards will just give you the formulas based on how long your beam is. But your beam could be 6 meters long, could be 8 meters long. It really depends on your project and what the architects have specified that this beam needs to be. Do you know what I mean? Or architect or whoever. A lot of things can govern like the length of how long a beam is, or I say beam, but like column, for example. So like a column height, right, would be its length vertically, and that depends on like the architect's like floor to floor heights and things like that. So yeah. Okay, so I'll explain what alpha C is. The basic idea. Alpha B. Sorry, I forgot the exact terms. It's been a while. The basic idea is you have to find these two things to find this. Okay, so you have to find alpha B, and you have to find lambda n. Okay, so let's start with alpha B because this one's actually quite simple. First, you have to check if any web buckling happens at all, right? Because if any web buckling happens at all, the effects are compounded, right? So I'll give you an example. For these sections, right, from the 250 UBs, you might start having the scenario where there's no web buckling because the shape is so stubby that, yeah, it just doesn't happen, right? But for any of these, you would have KF is less than 1, right? So that's for your 250 UBs, for example, and lower, whatever. And then this one, for example, would be for if this is like a 610 UB. Right. Okay, so let's talk about this one first. This, again, requires a bit of an understanding of the manufacturing process. But a lot of the time, you'll be dealing with hot-rolled UBs and UC sections, which just has a 0 for alpha B. Or what else is common? This one's pretty common, cold formed RHS or CHS. It'll tell you in the question, usually, like how it's made. If it's not obvious, this one's pretty obvious. Hot rolled channels would be like a PFC. That's called a channel section. Have you guys come across this yet in the lectures? PFC, okay. That's also hot rolled, but instead of an I, it's like a C. It's like 1/2 of an I. Okay. Yeah, and then there's just like different values basically. It's still 0 for this, but you know, if it's less than 1, then whatever, right? It's just gonna have. There's 2 tables you have to check basically, right? Okay, cool. So remember how we were talking about the member slenderness, right, before? Which was your effective length by radius of gyration, right? Now we have a modified version. So we have that, but we also have to multiply it by the square root of KF. Yeah? So if KF is like 0.8, the square root, I believe, wait, no. Okay, better example. If it's 0.64, right, your KF, I think the square root is 0.8. 0.8 times 0.8 is 0.64. So because all of these numbers are less than 1, because KF is always less than 1 or equal to 1, you always bring it closer to 1, if that makes sense. Right, so this number becomes 0.8. Maybe a number like 0.81 becomes 0.9. So you always bring it up closer to 1 by doing the square root. Okay, and then here we have square root yield strength over 250. So this one, because this is usually 300 or 350 or in that ballpark, sometimes 250 for a cold roll, for a cold formed CHS or whatever, but like, yeah, this number is usually greater than 1, right? So let's just say it was 1.21, right? So like this whole thing. When you square root that, yeah, it goes down exactly. So that goes to, am I dumb? I forgot all my, yeah, anyway, you get the idea, right? It goes closer to 1, whatever, point something. Yeah, that's right. But these are just kind of like modification factors that they came up with through like empirical experiments and stuff. Okay, that's effective length. I'll talk about a bit more in the next. Let me think about that. Next page. I'll talk about it more in the next page. Radius of gyration I kind of already explained, but it's the one that radius of gyration was the one that's square root of I on A. Yeah. And then there's Rx and Ry, right? So you have to check it in both directions. XX bending and YY bending, right? And then yeah, max slenderness ratio is the one that governs, right? So if we get a shape again that has like a really unbalanced slenderness ratio, you know that it's going to buckle in the Y direction, right? Like YY direction, or the minor axis, right? Like that. However, if we put enough restraints on it to change its effective length, it becomes a different story. Okay, so it's that ratio between the effective length. So remember when Farhan grouped this? It's the ratio between that effective length and the inherent shape's radius of gyration in the x direction and the y direction. So I'll show you what that looks like in the next slide. One thing quickly is this is from AS 4100 as well. The way that I like to think about it, there's something called KE factor, right? So effective length is your regular length, right? So this is the regular length, right? Multiplied by KE. So KE is the effective length factor. So what is KE? It depends on two things. The first thing is it depends on whether it's a sway or a brace member. Okay, so that might not immediately be obvious what that means right now, but basically, see if I can explain this quickly. Basically, okay, imagine my my fingers here, right? Imagine we have a rectangle which represents the shape of the outline of a house or something, right? And you apply a lateral force to it, like wind, okay? If it's unbraced, or if it's a sway, right, it does this, right? Okay. But if we have tension braces, like this, stopping my fingers from doing that, right, it has to stay in that shape now, okay? So that's braced, what I just drew there, that's braced now. So in the case of braced, what happens is when you have loads, let's just remove, forget the wind thing for a second, right? When you have a braced shape, right, and this is a column, and this might be like a beam or something, let's forget the floor. Right, so we're just focusing on this column, right, but it's braced, essentially, and then it's connected to like a rafter or whatever. And there's an axial force happening on this column. What's essentially happening is it buckles like that, right? Because it, like at the top, it can't move left or right because it's braced. Okay, but if we had that first case, right, the whole building can sway to the side. So effectively, it's cantilevering, kind of, from the ground, right? Which means it can buckle to the side like that. That column's cantilevering, right, from the ground up. Does that make sense? Okay, so that one's sway. So when we're talking about this member, think of it, it's easiest things to think of it like in terms of a column, right? The column for this building, is it braced or is it sway? And it all depends on the overall system's stability, right? Whether it's been braced using, this is called wall bracing, or not, okay? And this isn't terribly uncommon either. What happens in a sway frame is it might be an I-beam that's got its flanges that way. Do you know what I mean? So it's just got its major axis bending is the, sorry, I'm kind of like going too far forward, but like the column can be orientated to resist bending in that direction that is the sway direction, because it needs more help in that direction. You know what I mean? But then, yeah, anyway. Yeah, okay. I'll shut up because it'll come up later in the course, basically. Okay, next thing you have to realize is, I like to think of it like, what's the size of the C shape, right? The deformed C shape. So once you have that axial compression on this column, and it's braced from the top and the bottom, it creates a C shape. Okay, the C shape in the case that I just drew over is 100% of the length. Yeah? So LE is L, because K is 1. Okay, but what about here? It's fixed at the bottom, but pinned at the top. This is 85%. The C shape's 85% of the length. Okay, what about if it's rigid at both the top and the bottom, sorry? This is the idealized end constraints method. So this is a good ballpark of what it would be, but there's actually a way to calculate it, which you learn in the last week of the course, called the gamma method, and you can figure out this exact KE value. But this is the right ballpark for a quick first pass analysis, which is all you need for this week. So that's 70%. Okay, so that's the brace cases, right? So it's simply supported, basically top and bottom. So for sway member, it gets a bit harder to think about, but that C shape, so it's fixed at the bottom, right? That C shape's actually, is more like 120% of L, because nothing's stopping it from becoming more and more swayed, right? And then so that thing at the top, it's like this has to be 90 degrees or whatever. That's what that's saying. But it can still sway. But this one, it can be whatever angle, right? This one, it's like a completely, truly cantilevered end, right? And then that results in a C shape that is 220% of the overall length. Sorry? Going back to this example, it would be like if you had columns that could go like that. But imagine the beam that was connecting them was super rigid, and that can't change shape, right? And we know that this is rigidly connected together, so that has to be 90 degrees. But if this was floppier, not just welded, but like yes, but also this has to have a super high inertia. That's probably more so what it is. So imagine like a really, really deep beam as the rafter or something, right? Would be in an ideal case. Whereas you might get something more like that if you have a low inertia for this beam, right? You know what I'm saying? So it allows rotation here at that corner, even though, I didn't really draw that well. because that has to be 90 degrees if it started at 90 degrees, because that's what a rigid connection is. Yeah. Okay. I don't know if I drew it that correct on that side either, but I think on the left I drew it correct. Okay. Yeah, and then here, the super rigid beam thing, but it's pinned at the bottom instead. So that allows a huge amount of, like a big C shape as well. Okay. So, yeah, that's basically that. Okay. Other thing is sometimes it can be braced in one direction but not the other. Okay. So Gemma Farhan and his hand and all that. So if his hand was holding it that way, his hand was holding it that way, but it's kind of the hand holding analogy for like a brace. Oh, sorry. What's the word? Yeah, for a brace, like stops working when I'm talking about like a human holding it. But like basically in structures, you're gonna find that sometimes another member that's like basically like bracing it is only gonna brace it in one direction. So for example, if my hand is bracing it this way and it locks it in, and it can't go like this way. Say like my elbow is like fully rigid, but for whatever reason it can go left or right. That's when it's braced in one direction and not the other. So you kind of have to think about that, if that makes sense. Because what often happens a lot of the time is you get something like this, right? Say the x-axis is a stronger one. Say it's like that, right? And it's doing x-axis bending, like down. It might be not braced. It doesn't, like, as it bends, it does like a full C shape down, right? But if it bends the in and out of the page, it might be braced in the middle. Because usually bracing is there to support the weaker direction. Do you get what I'm saying? So bracing usually does like this. So that's LX for it's like the entire beam length, but LY might be half the beam length or something. Because there would be a support holding it in the middle, basically. I hope that makes sense. That wasn't that good of an explanation, to be honest. Okay, we'll come back to that if you have questions. Okay, radius of gyration. I've talked about this a little bit, and these are easily found on OneSteel, by the way. So if you have a finished section, or if you have a standard section, it's actually very easy. Sorry, that's the root radius. Radius of gyration is over here. That's Rx, and that's Ry. Okay, so let's just talk about an I-beam for a second, right? So it looked like that, you know. A 610, we have a radius of gyration of about 250 in the x direction, but only 50 in the y direction. So it's 5 times weaker at resisting buckling, global buckling, in the y direction than the x direction. Yeah. So just to give you an idea of the numbers, basically. Okay, so with that in mind, we haven't even finished, right? So alpha C is what we're looking for the whole time, okay? And the way that you do it is first, you find that modified slenderness ratio. Let's say it was 100, right? So that's that whole thing, that this whole equation, to remind you. This one, you punch in everything. And then you also make sure that you get the max between the x direction and the y direction. And you get whatever it is, the max one. Sorry. And then it's a UB. And so if you remember that table, for a UB, alpha B was 0. So that's this one. Sorry, I'm something on my throat. So what you do, you go to 100, you go up until you reach 0. So that's the line for 0. And you bounce left. And that gives you 0.55, for example. Sorry? It's 100 times easier to do it graphically than by the formula. There's a formula. It's fucking AIDS though. I won't even show you it because like I've never done it without graphics. It's in the lecture slides. There's alpha A. There's alpha there's like all these weird Greek letters and shit. It's not worth doing. Just do it graphically. It's 100 million times easier. Yeah, but then that gives you that. That was from the previous part, and you can work out whether it works. Okay, one more thing I want to talk about. Imagine your capacity as a health bar, okay? So your HP. Over here is NS, right? Which you calculated. So that's how much it can take, how much the section can take in terms of capacity. Let's call it 0.9 because of the capacity reduction factor, right? So your loading, which I'll do in red, might be like this, right? And it might be able to, let's say, reach 95% of this, right? Your capacity. But then you do your calculations for NC, and you find NC is less. Oh, sorry. Yeah, NC is less than NS. Does that make sense? Because this is a reduction factor. It's always going to be less than. So this might be like 80% or whatever it was, right? So that example I gave you before, it's like 55%. So because of Euler buckling, our section's actually gone down all the way to here. So it's lost 45% of its capacity, right? So that would be something like, this is a very extreme example, but that's something like this, right? The slenderness that we calculated has caused our yield capacity, like our squash capacity, to be reduced by over 50%. For this, it would be even more. This is reduced by like 99%, you know what I mean? Because could you imagine, like, I cut off like this small bit of the timber, and I compress it. It'd be really hard to squish, right? But this is super easy. I could break this easily by just squashing it. But the actual like compression capacity is as if it was like a tiny little block. Like how much force before it gets crushed. You know what I mean? All right, that's pretty much all I had to say.